So as you might guess from the title, I'm going to be talking today about modeling games of cards in CSP, or in other words, in a language for concurrency. And I'm going to be doing so in such a way that we can use model checkers potentially to solve these games of cards, or to show when they're not solvable at all. I had some excitement last night because I discovered that the LaTeX package I've been using for the last 15 years to build my overheads suddenly stopped working, I guess because of some change in LaTeX or some change in the text setup back in Oxford. And so I had to hurriedly reformat them into this Beamer style here. They look all right, I hope, but they're not very sophisticated. So a few words of explanation first, because I guess that a lot of you will not know very much about these topics that I'm going to talk about today. What is CSP? It's a notation known as a process algebra. A process algebra is a particular sort of algebraic, surprise, surprise, notation for describing concurrent systems. And the process algebras typically concentrate on process algebras by specifying and describing patterns of interactions between parties. They tend not to work by a shared variable style model of concurrency. Rather, they work by typically handshaken interactions whereby parties perform some action at the same time and thereby achieve a communication or synchronization between them. The CSP process algebra is one of the two original process algebras that were developed concurrently in the late 1970s. CSP was initially developed by my doctoral supervisor, as Peter said, Tony Hoare, and I joined in the project in 1978, which was just as Tony published his first paper on CSP, which was a CSP not of the process algebra, but the process algebra version was what I and some more students and Hoare then basically developed. It presents processes in an algebraic style using ways of, as I say, specifying patterns of interaction. And these patterns of interaction might be ways of describing sequential processes, which, should we say, offer individual actions. And here, E is some specification of one or more actions that are performed before the process behaves like P. It can offer choices between behaviors, as with these two operators, which offer different sorts of choice to the rest of the world about the actions of two different processes. And you can find ways of putting processes in parallel with each other, either in pairs or in groups. CSP is also a mathematical theory for reasoning about concurrent systems. It allows us to prove that they have certain properties, or perhaps disprove that they have certain properties under various assumptions. The various ways in which you can look at the mathematics of CSP and other process algebras, and in particular CSP can be given either an untimed semantics, in which you simply look at the order in which actions happen rather than the exact times, and correspondingly it can be given an exact time interpretation. For the purposes of this talk today, I'm going to be concentrating almost exclusively, or perhaps exclusively, on the untimed view of the world. You can describe CSP via an abstract implementation, which is what an operational semantics is. You can describe it via the set of algebraic laws the language satisfies, which is what an algebraic semantics is. But the particular tradition in CSP is to imagine different powers of observer observing a particular process and seeing what that observer could record. So, for example, the traces of visible actions that the process might perform, and then to base the equivalence of processes on the equivalent views of one of these particular observers. And that gives us sort of mathematical models. But again, we're not really going to be touching very heavily upon that today. And these models give rise to notions of refinement between processes. So you can say that P is refined by Q if everything that Q does is permissible for P. And these can both be used for what you would think refinement would be used for, which would be sort of compositional development or incremental development of a system, or, for example, for comparing one release against the previous release. But also, and this is a very heavily used possibility for CSP, where Q is some implementation or some model that you want to test, and P is a simple specification which establishes some property that you do or do not want to hold of Q, and by testing the refinement you can find out if it does. So for the first decade or so of its life, CSP was entirely a vehicle for theoretical musings and toy examples, but when there started to be machine automated tools for reasoning about CSP programs, all of a sudden it became a practical tool for developing and verifying real systems. In order to make it machine accessible, we had to turn what, if you look at it in sort of abstract books, looks like a very abstract mathematical notation into something which was, should we say, both machine readable easily, or easily writable to be machine readable, I think more precisely. And secondly, it was a useful programming language for actually specifying real systems. And that's what CSPM does. M, unsurprisingly, they're standing for machine readable, I guess. So basically, that's the language in which all the examples I'm going to be talking about today are phrased. And it's the integration of the sort of operators we saw on the previous slide for describing parallel interactions into a Haskell-like functional programming language with basically lazy semantics. And the functional programming is used to define data types, operate on the program data, such as the data you send around as part of communications, or which you hold as parameters in programs. And also to lay out complicated processes and network. The only real difference between the programming language into which CSP is embedded here and sort of usual styles of functional programming is that CSPM contains mathematical sets, that's to say unordered collections of objects where multiplicity doesn't count, as primitive objects, because essentially sets are very commonly used in the Blackboard original style of CSP. So this is just a very simple example of CSPM, representing an important example that Peter and I worked on 20 years ago, which is the model of the intruder, which we developed for interrogating cryptographic protocols. So this simply says that our intruder model SPY, of course, it applies this chase operator, which is a sort of compression to make the model go faster. And then for every fact, every X in F, where these are a set of facts, you put together a process which is ignorant of the fact. In parallel, where of course they've all got different ways to learn these facts, and they also allow inferences to happen between the facts, but you hide the inferences. So I'm not going to go on any more about this example. It's just to show you a simple example of, well, as you said, concise, but a subtle example, shall I say, of the programming style. FDR, which stands for Failures, Divergences, Refinement. Failures, Divergences being one of the most important mathematical models of the sort I talked about a minute ago, is a tool which we first developed for an industrial application back in 1991. That particular industrial application was reasoning about the communications hardware on a microprocessor. And this is a refinement checker, but most people would view it as one of a large class of tools called model checkers, which I can talk about a bit about in a moment. But basically what it does, with one or two other bells and whistles, is it tests for refinement over some of these models that I talked about earlier on. And it's developed continuously, more or less, since 1991 at Oxford. It's currently in one of its most rapid development phases, having gone fallow for a few years previously. A model checker is a verification tool which could apply potentially over quite a large range of input notations. But the things that these input notations have in common is that you can interpret them as describing programs or state-evolving systems where they can progress through different actions, different external stimuli and internal actions through a wide variety of states in the way that they execute. And you want to show that every one of those states satisfies some property appropriate to the particular point in the execution which it's reached. In the original formulation of model checkers, the properties that you are satisfying were formulated in a formal logic, and so FDR sits sort of a little bit at the edge of that range in the sense that we're now formulating the property in terms of another process in the same language and in terms of refinement. But in terms of what it actually does, it very clearly is a model checker. FDR allows us to check processes for errors in the traces processes perform. It allows you to check that they really will do what you want them to do, and in particular won't do something like deadlock. And that it won't live lock, which means to say it gets into a state where it performs an infinite number of internal, invisible actions without doing anything useful on the outside. FDR can also check for various forms of non-determinism, meaning to say a formally and mathematically specified, usually, concept of unpredictability, or we cannot be sure what this process will do in a particular circumstance. If you look at the range of model checkers there are around the world at the moment, and there are a lot, you will find that they're split into ones which essentially work by explicit state enumeration, which is the class in which FDR mainly finds itself, and the class which reduce the problem that they're trying to reason about into a typically propositional calculus expression, and use propositional calculus tools to decide whether or not the property holds. And the most common form of propositional calculus tool to use is a SAT checker. That's to say, is a particular proposition formula satisfiable or not? I mean, basically, almost all model checkers are essentially trying to prove or trying to solve one NP-complete problem or another. But just the builders and users of these tools have confidence that most of the cases that these tools are going to encounter really will not behave as badly as that complexity class suggests. And I think certainly these tools have been one of the main examples in the last 20 or 30 years which have convinced a lot of people that NP problems aren't all bad. Explicit state enumeration means basically it goes through these states one after another. And we're talking here of many, many states, and we'll start thinking about the numbers in a minute. What concurrent systems, as expressed in a language like CSP, typically exhibit, unfortunately, is something called the state explosion problem, meaning to say that as you make a system bigger, in particular as you increase the number of parallel components to a system, typically the number of states that that system can go through in its executions grows exponentially. And unfortunately, whereas, as I say, the NP completeness in a large number of instances proves to be not too worrying a dragon, the state explosion problem really does happen and really does get in the way for a large number of interesting examples. And so over the years, people have invented all sorts of techniques for getting around it. And of course, stat checking was one of them. But in a more explicit world, there are others, such as partial order reduction, meaning to say you don't actually visit all the states, but you visit enough to somehow demonstrate that you will find an error if there was one. Compression, which means to say you look at subsystems before you put them together and try to reduce how many states these subsystems have. And data independence, which is where you look at the parameter data types of your system and you try to show that it would be sufficient to look at a much smaller one. Those and more are commonly used techniques across classes of model checkers for countering the state explosion problem, and FDR sometimes in multiple ways incorporates all of these. It compiles a network specified as a CSP expression into explicit representations of all the sequential component processes, and it also generates from that network rules for combining together the actions of the components into top-level actions of the entire system. And in fact, the concept of a supercombinator is the major driver of the speed and efficiency of FDR. It turns out, in some sense, FDR has a large but nevertheless finite sweet spot amongst what sort of CSP processes it will handle, which is driven primarily by the efficiency of this particular operation here. And the way that supercombinators are implemented and the sort of states that they operate on allows fast execution and compact storage for the state spaces that FDR generates, because despite the use of these techniques, which all have the property of cutting down the number of states that you visit overall in a check, sometimes you are visiting many billions of states in a particular check. FDR can be used either in a standalone mode, and I'm going to show you operating in that mode this afternoon, or as a back-end for other tools that auto-generate CSP. Given that FDR has evidently been around for 24 years, it's perhaps surprising that we've only reached the third main version of it. The first version, which was unsurprisingly just called FDR, was around basically from 1991 to 1995 or 6. Then FDR2 was released, which was around until about 18 months ago, and now it's been overtaken by FDR3. The latest version, although I remain nominally in charge of the project, was actually developed mainly by Tom Gibson Robinson, who's an RA working at Oxford. And depending how you look at it, it's either very different or very similar to FDR2. For those actually approaching the use of it, it has a brand new GUI, and instead of operating on it via a scrolling terminal view, if you're actually driving it from another program, it has a proper API to run it from. The most important difference to people actually using it on their scripts that they already had is that it's now implemented itself to run in parallel on multi-core and cluster systems, which FDR2 wasn't. At least only very sporadic versions of FDR2 that weren't properly maintained occasionally ran on these things. But it's a fundamental part of the operation of FDR3, as of course it has to be in the modern world of computing. We believe we did the largest explicit model checking run ever tried, which took us on a 1024 core cluster, which was a cluster of 64 16-core machines that we rented for a few hours off Amazon for about $100. We ran 1.2 trillion states of an explicit check in 4 hours, and it used about 6 terabytes of the memory of that cluster. We also had a 1024 core cluster available to us on an Oxford supercomputer, but unfortunately that didn't have enough memory to run this particular check on. But if anybody's interested in the parallel performance of FDR, then Tom and myself and other people have had sort of 2 or 3 papers on the development of FDR3, and in particular on its parallel running model, which contains a lot of examples which you can read about, and also, of course, download and try for yourselves if you've got an even bigger cluster you want to try it on. But if you do have an even bigger cluster, then do let us know what the results are. There are, of course, as well as these 2 obvious things, improvements and extensions across a wide range of functionality. For example, this is something we've implemented only relatively recently, which is why it was at the front of my mind while I wrote this slide. It's got the first efficient algorithms which directly compute a compression function, a state compression function along the lines of what I was talking about in terms of reducing state spaces on the previous slide, called weak by simulation. Weak by simulation is extremely well known, but apparently there were no decent algorithms for computing it. But we sat down and actually worked one out, and it now runs, well, on many examples, actually faster than strong by simulation, for those of you who know what that means. Another big improvement in FDR3 over FDR2, at least for most people, is the incorporation of a real type checker into the compiler that compiles the CSPM for it. It makes the programming a much more accurate activity. The only reason why you might not like the type checker is if you're trying to get through some old scripts that FDR2 managed to accept, even though they weren't completely type correct. And almost invariably this was because FDR2 wasn't actually using the bits that weren't type correct. So FDR2 did all its type checking on the fly, so to speak. Anyway, you'll see FDR3 working in a minute. Of course, for a tool that's been around as long as FDR has, it's had many, many users over the years. It's been used in many student projects, obviously, many doctoral theses, in many industrial uses as well, or in many pieces of research by people. It can be used for verifying or refuting distributed algorithms, or actually one of the main uses of it in respect of distributed algorithms is that if you come and try to implement a distributed algorithm you find in a book to see if it works properly by programming it into CSP, the first thing you usually discover is that the distributed algorithm in your algorithms textbook is horribly underspecified. There are a tremendous number of cases where it doesn't tell you what you have to do. But surprisingly often you find subtle cases where well-known distributed algorithms don't work. If you look at my more recent book on CSP, which is called Understanding Concurrent Systems, I could do a detailed analysis there of something called the Bully algorithm and find that a perfectly plausible implementation of that, which is, by the way, a timed algorithm, a timed fault tolerance algorithm, doesn't work. The same is true of large numbers of supposedly secure systems, for example. And indeed, the area I first got into security was through model checking supposedly secure systems on FDR and finding, along with Peter and lots of other people, and especially Gavin Lowe, that very often supposedly secure protocols were not secure by running them through a tool like this. Many of the industrial applications of FDR have been in real-time systems, such as many of them in areas like avionics, and in fault tolerance. Because what a model checker does is it searches through all conceivable patterns of behavior under all allowed patterns of events that happen from the outside, and so checking if, should we say, fault tolerance conditions can conceivably go wrong is an obvious sort of application for it. And many people, including myself, have produced mappings of other models of concurrency, such as shared variables and multiple notations for describing embedded systems, such as, indeed, multiple versions of state charts into CSP for running through FDR. And these have frequently been modus operandi of industrial applications. There have been many industrial applications that I haven't personally been involved in, but these are ones where I have personally been involved in and can therefore talk about with a bit more authority. Verum is a company which has gone through some internal difficulties of late, but it did have an extraordinary technology, and I suppose still does. Although who owns and runs that technology is now more disputed than it used to be. But what the technology they had was to develop a language for building the sort of state machines that people like to describe embedded systems in, and then auto-generating code from those systems after verifying a CSP model of the systems. So typically they could generate embedded code which would run up to of the order of 1 million lines of code, which had been verified on FDR by means of their technology, and the size of systems that they could manage was truly impressive. DRA or DERA, whatever it was called, now become Kinetic, which is where Peter worked when I first met him, back in the sometime in the early days of the 90s or something like that. Have a very long history of using FDR and CSP in practical examples. But everybody doing that sort of thing at Kinetic decided that they didn't like the new company culture. It was basically a civil service organisation that ultimately was privatised and took on the extremely sensible philosophy, I think, for a company that actually doing research is silly, and that they just want to rely upon the productivity of their managers and their existing IP. Does that sum it up, Peter?
Seems fair enough.
At least that's the attitude they take, and so everybody who's actually doing any research there, at least in an area remotely close to what Peter and I used to do, has now left. And some of them have left to basically take over the style of business that was being done here in a company called D-Risk. So whereas here code was being verified correct by design, what these people were doing is typically taking legacy code or code that had been developed by other parties, and then finding ways of running that through FDR, frequently by means of things like state charts, but also ways of compiling various dialects of C, for example, into CSP, which always surprised me. I see I've misspelled avionics there, but I'm sure you know what it means. So a large number of things that either went or potentially went bang were verified through FDR, which is I'm not sure if I'm proud of that or not. I suppose I should be. Quite a number of companies use FDR and its ability to generate lots and lots of traces as ways of generating test cases that they could run through other systems. But in just about every, not every, but just about every industrial application that I've come across personally, so certainly everything that was being done on remotely a production line scale, certainly was happening here. These tools always, these methodologies always worked by automatic translation of other notations, such as state charts into CSP. So the current strategy for developing FDR is, first of all, I would love to be able to handle software better. In other words, get further away from sort of hardware-ish models with small variable ranges and that sort of thing, which is what we're good at handling at the moment. Symbolic execution and symmetry reduction is a current priority, and we'll see why later. Lazy compilation, which would help us to get away a little bit from the restrictions of the supercombinator model by allowing us to handle some larger component processes. At the moment, the thing which takes most of the time, most of the time, are parallelized in FDR3, but there's certainly potential for parallelizing more of these things. For example, the compression functions are not currently parallelized, at least in the delivered version. Our current theme of ours is to get away from explicit model checking and use local analysis of networks, for example, for deadlock and for live lock, by looking to see when you can do local analysis of the state spaces of the individual components and their interactions with the locally surrounding network components, and then piece these interactions together into arguments for why the complete network works, or perhaps find ways in which it doesn't work. We successfully produced a tool which does this for live lock, and we're currently doing some very successful experiments which illustrate doing this for deadlock. And in each case, we actually make use of SAT checkers of the sort I was talking about earlier, to actually basically hunt for proofs or disproofs of assertions about graphs of local interactions. There have also been several experiments in the use of SAT checkers for replacing the explicit enumeration functions that lie behind FDR, but in each case they have not been successful, in the sense that although they worked, they proved in the great majority of cases to be a lot less efficient than the rather basic methodology of running through a state at a time, which came as mainly as an unpleasant surprise, although it did sort of justify our having stuck to the, in some sense, more obvious method for as long as we had. I have, in the last few years, generalized the input notation from FDR, potentially, from the CSP language itself to a wide class of operational semantics which are sufficiently close in some sense to CSP to be directly amenable to the way in which FDR works and the semantic models that it runs on. And so that should provide soon, I hope, a direct way of people compiling other notations into FDR rather than doing so via translation into CSP. So now let's start to look at some of these games and card games. I've long liked to use games, by which I mean sort of mathematical puzzles, finitely expressed, as benchmarks and demos for FDR. I mean, the one I'm best known for probably is peg solitaire, which is where you've got a cross of pegs and you want to try and get them all down to one. I've also written about variants on Sudoku, and I've used many, many examples of examination questions over the years, such as magic squares and all sorts of sliding peg puzzles and so on. And I like these because people recognize the difficulty of the problems being tackled, whereas if you provide them with some sort of rather dirty-looking program, how do they know that's genuinely difficult? But they certainly haven't tried to solve it themselves, have they? And you can usually, because of the way CSP works, produce elegant and succinct models, typically because of the functional programming which is built into the CSPM notation, but also very importantly because CSP supports multi-way handshaking, which is vital in almost all of these models. You see, other process algebras tend only to allow pairs of processes to synchronize, whereas CSP allows as many processes as you like to synchronize on a single event. And as we'll see today, we can illustrate some interesting coding and specification styles. But the logics which underlie CSP models restrict us to single-player games. That's to say, whereas one player is trying to achieve some goal, as he or she would be in solitaire or in Sudoku, rather than looking at multiplayer games where people are opposing each other, because the models that CSP works on are linear time rather than branching time, and you need branching time where you look at sort of possibilities leading to multiple other possibilities, which is a very different sort of technology to reason about multi-party games. And many games are scaled naturally to create smaller or bigger versions of state spaces. They also tend to illustrate state explosion all too well. And just an example of this, the standard if you don't mind me moving over here for a minute, the standard PEG solitaire board has got 33 slots in it in an arrangement that looks like this. Honestly, there are 33 squares there. And if you analyze the puzzle, you find it's got 187 million states or so, which was an awful lot for many years for FDR, but now it's nothing. But if you add on 3 extra pegs up there, and you might do this because you find that 187 is now too small for doing your benchmarks with, all of a sudden you find you've got 1.5 billion rather, states. And if you added another 3 here, say here, you find you've added on, well, you multiply it by 8 again, more or less, and you now find that you've got just under 12 billion states. And every time you added another 3 slots like this, you find you've multiplied it by 8 or nearly so. So it's very easy to create systems as big as you like, but it's also very easy to illustrate the awfulness of the state explosion problem by doing that sort of thing. I think the one I've now drawn is probably the biggest one we've probably bothered to run. We certainly could run the one which is nice and symmetric and has got 3 on each side like that. The reason, by the way, that I had them on in groups of 3 is all to do with the theory of the game of solitaire, and that by adding on a group of 3 pegs like that, you're very likely going to preserve solubility. Anyway, I've tended to do that a lot over the years, but I've never looked at card games before. Card games suggests, or if I got a card game with a 52 card pack, it suggests that a lot of the time I'm going to be looking at 52 processes, or perhaps slightly more processes than that, to deal with all the cards with perhaps 1 or 2 bits for managing the game. And certainly the range of deals of a pack of cards is somewhat forbidding when you think about it, even for a modern checker that can handle a trillion states. A trillion is nothing compared to 52 factorial, of course. But the way card games work, if you actually try it out, means that they go through, as long as you model them effectively, far, far less states than that, although still a lot. As I said before, FDR is not suited to games with opposing players because of the use of linear time models, so that we've got to restrict to single-player games. In other words, games of solitaire or patience, as different people call them. Individual game deals of patience or solitaire games as puzzles for a single player. And we're going to see a few of these games in a minute. And of the ones I've tried, typical deals are usually comfortably within the state space range of FDR, rarely more than 1 billion, as long as they're modeled sensibly. But it tests the other capabilities of FDR in terms of dealing with complex component processes and complex patterns of interaction. And this often occurs because of the potential mobility of cards within games, as we'll see in a minute. Mobility in process algebra means the ability to handle the processes that move around. So rather than stick in one place and communicate with the same group of neighbors all the time, as happens on a solitaire board, because in a solitaire board we typically might model 1 process per slot, which always has got the same neighbors. If we model 1 process per peg, then they would be mobile. But all the models I've ever done of solitaire have been 1 process per slot. And mobility as a concept is often coupled with the concept of dynamic networks, where processes can be created and vanish again, as well as rather than just static networks where you've got a constant set of processes around forever, all communicating in the same patterns as they always have. So the former, in other words, handling processes that change their communication partners, is not an obvious match for CSP, where parallel processes tend to have, in fact, do have constant alphabets that they communicate with for all time. And the latter is not an obvious match for FDR, which naturally handles fixed or at least bounded size networks. However, the other main reason why for a very, very long time we didn't consider mobility in CSP, is that there was a very successful calculus of mobility called the pi calculus, developed by Milner, etc., which was a development from CSP's main rival called CCS, which has been around for a very long time and used in all sorts of applications as well, such as, for example, protocol checking, again, at least in a modified version. But it doesn't have tools with the power of FDR, and many people who were big users of FDR complained that we didn't support them in their mobile activity. However, since people have started to complain to me along those lines, I've actually shown how to completely simulate the pi calculus in CSP, but in a rather abstract way. And I've also proposed a mobile variant of CSP with sort of some bounding limitations in my most recent book. So the mobile CSP fully supports mobile channels, but will only work on present FDR with a bounded collection of processes. We'll see little hints at mobile CSP later on. Mobile versus static card game models. A mobile one would be where you've got card processes that move around, changing their neighbors as they go. Interaction with neighbors, interpret the rules, implement the rules of the game. So in other words, you can only move on top of a card that you're legally entitled to move on top of, and things like that. A static model of a card game would look much more like the solitaire model I was hinting at a minute ago. In other words, you would have a process for each of the places where the cards are put, taking different values when empty or with any one of the range of possible cards in. And again, you'd have to implement the rules of the game somehow in your model, just as one does in solitaire. I'm going to talk briefly about 4 different games of solitaire here, which are the 4 I've actually experimented with. I imagine that many of you will have played Idle Moments on at least several of these on your laptops. Klondike is perhaps the best known, I think, game of patience, where you deal out 1 to 7 cards like this and have what's called a stock of cards that you deal over, and you build up columns of cards in alternating reducing value. So you can put this jack on top of this queen here, and then you could potentially put a red 10 on top of that, and so on. And then you build up the 4 suits here. Is anybody here not familiar with that game? I bet not many of you are familiar with this one. I chose it because it was a natural bridge between King Albert and Freecell. It's named after a king of the Belgians. And as you see, it looks rather like a game of Klondike, except there are now 9 columns and the cards aren't turned over at all. And instead of having that stock with what's called a reserve, or sometimes it's called a Belgian reserve in the literature. And so basically you use this like the stock, except that you can always take any card out of this whenever you want to. And the rules are very, very similar otherwise to Klondike. But it's similar to Freecell in the sense that no cards are initially upside down, and you don't have to deal out the cards one after another. It's actually rather easier to program than Klondike. Freecell, again, is one which I bet everybody here has at some point tried. Well, again, the rules are somewhat similar. You try to build up cards in these alternating, decreasing columns here. And instead of the reserve or the stock, you now have these 4, typically, cells in which you're allowed to move cards into and out of to sort of make way for other ones. So these first 3 games I regard as a particular class, whereas the last one was my favorite game of patience when I was a boy growing up, and doesn't work in the same way at all. How this one works is that you deal out all the cards into a 13 by 4 array, as you see here, but you take out all the aces and throw them away. Well, at least put them on one side. And that leaves 4 gaps, and you can always fill a gap with the card which follows the one to the left of it. So I could put the 6 of spades in here, taking it from wherever it is, taking it from here, and then I could put the 8 of spades in here, and so on. Whenever a gap appears at the left-hand side, like this, you can fill it with a 2. You see 3 of these are already filled with 2s, and I think there's one up here somewhere that I could put into here. And the object of the game is basically to have all 4 suits arranged in the 4 rows, like this. That's a game which I didn't know the name of for most of my life, but I had played it a lot as a child, and I eventually discovered via Google image search that it was called Montana. The card configuration of free cell is not naturally static, because cards move around, and there are going to be cards at some places now, to a very large extent, where there weren't cards before. If I build up one of these columns or take things away from these columns, then the range of places where cards are is itself dynamic. If you actually try to do a static coding of free cell, you get into big trouble. And the reason why you get into big trouble is because if you've got a soluble game, and almost all games are soluble, you can actually permute the columns that are at least all in descending order arbitrarily amongst these 8 columns, which gives you a factor of 8 factorial in a static model over a dynamic one. Because in a dynamic model, you can just in a dynamic model you can simply have the columns arranged below a certain card without having to worry about exactly where they are. And you find that by moving to a mobile model, you get a far, far more efficient, as I say, up to 8 factorial times more efficient in terms of state space one, over the natural static one. So therefore, what we do is use a process for each card with parameters to hold links. That's to say the cards that they're close to. And of course, this is the element of mobility. As they're mobile, these links change from time to time. In addition to the 52 card processes, we also have counter processes for the number of empty columns there may be at any given time, how many empty free cells there may be at any given time, and use the process to monitor the progress of the 4 suits that we build up, looking for a solution. A card has got separate states for being in a suit from which it cannot move. A free cell from where it can move to a suit or to a column, or in a column where it's got parameters to register what's above it and below it, because it needs to have that information so the game rule can be properly implemented. Clearly it can move to another column, it can move to its own suit when the suit's in the right state, and it can move to a free cell. I can do all of these things in a column only when it's at the top of the column, because that's the rules of the game. And you can limit the ranges of some of these parameters because of the structure of these stacks. So instead of being the full range of 51 other cards, we can typically cut a lot of these ranges down to say 3 or 4 cards, which is extremely useful in the coding. In these card games, I've wavered between 2 different styles of modeling mobile code. I model them in sort of straight-up conventional CSP, where they're potentially connected to any card, but the links tell them exactly which one to communicate with, and where the alphabets are much larger, or a sort of truly mobile style, where, for example, the link channel, which would be a single link channel of a particular card C, would be passed from one card to another, depending on which one it was linked to. Mobile CSP of that style is not directly supported by FDR, so we need to create the conventional CSP representation of it, and you'll see and described in my book just how to do that. In fact, my favorite coding of free cell is based on the former. That's to say, not using mobile CSP per se. So let's go and run this. So it turns out that free cell is actually a very, very soluble game. The literature on free cell is extensive. The fact that it's incorporated in Windows has, I think, led to this. Microsoft brought out 32,000 sort of initial games, which are seeded by a number you type in. And of those, as it turns out, all but one are soluble. With 4 free cells. Most are indeed soluble with 2 free cells, and some with 1 free cell. This particular one I've got here is soluble with a single free cell. The fact that a check has passed here means to say that it didn't find a solution, because what we actually specify here is that the puzzle has no solution. What this says is that it cannot communicate the event which would happen if the puzzle were solved. So the fact this check has passed means that there is no solution. The fact that that one has failed implies that there is a solution. And if we press the debug button, we can do that. But I can actually, I'll run all those again by just typing in reload. And now I can check. I can do the first one. That's to say, what happens if you give it no free cells at all? It's spending all this time at the moment compiling up its representation of the network. It's not running the check per se. It's just compiling up its representation of these 52 different card processes and a few others. And so it took no time at all to find that there was no solution to that particular highly restricted game. But if I give it 2, if I give it 1 free cell rather, you find it does find a solution in 62 moves here. And if I give it 2 free cells, you'll find it takes longer to find the solution, but finds a shorter one, which I suppose is not surprising. Because, of course, anything it could do with 1 free cell, it could do with 2 by not using them. So it can do more things now. But equally, there are more possibilities for finding shorter solutions. So you find this is taking longer. We can see how many states it's gone through at any particular moment. But it will fairly soon now find a solution to it, I hope. I'm not going to run the 3 or 4 ones, even though I have done, because of course they'll take even longer, and find even shorter solutions. So what this graphic is showing you here is how many states there are in each of a breadth-first search of the reachable state space. And they get wider and wider because in this particular check, as in many others, in the initial part of the check, you get more and more states reachable in each ply until finally you either find a solution or it starts to go back down again as you reach the end of the check. Of course, if anybody wants copies of the files that I'm running here, they're very welcome to them. One thing I should say about FreeCell is that those of you who've actually run computer versions of it will be familiar with the idea that it allows you to move more than one card at a time if you could do it in individual moves. So, for example, it will, if you've got all 4 free cells empty, it'll allow you to move up to 5 cards as a column from one column to another, for example. My implementation doesn't do this because, as I say, the rules of free cell are basically just you move single cards, and the implementations that are supplied are just sort of optimized to allow you to do things quickly that you could otherwise do. Of course, I could have implemented these multi-card moves too. It's just I haven't bothered to do so, and it wouldn't change the solubility at all. This is taking slightly longer than I expected. I suppose it's because I'm here running on my laptop, which is an underpowered machine compared to the bigger computers back home I tend to run these things on. So it will be quite straightforward, for example, though I haven't done it, to produce a version of free cell in which you're not allowed to do any explicit moves into the free cells, but could do any move from one column to another or whatever that the standard implementations would allow you to do. So you just have to implement the same rules as before. Come on, we must be getting there soon. Maybe I'll tell you what, I'm going to leave that running, and I'll show it to you later. If anybody wants to have a go at a game with no solution, then if you try number 11982 on Windows, you'll find it has no solution. I have another example file which illustrates it. King Albert is closely related to free cell, as I said before. The coding is very similar to that for free cell, and you've got exactly the same reason why you have to do it basically in mobile fashion. Whereas free cell was very well studied, evidently King Albert hasn't been, because the literature you find online suggests that only 10 to 20% of games are soluble, whereas in my models I found that somewhat over 70% were soluble. Of course, for free cell, all I can do is reproduce the well-known results about it, whereas for other games, you can sometimes be more original about your results, although, of course, again, Klondike has been very well studied because it is so well known. The interesting thing about Klondike is the difference between the free cells or the reserve on the one hand, and this stock that you keep turning over on the other, because what the stock really requires is a doubly linked list from which you can delete things, because you want to turn over this stock, and you want to be able to keep turning over in one direction, and you want to keep on taking cards off down the stack in the other direction. That's hence the reason for the list being linked in the other direction. And of course you want to remove cards from it. And that actually is a reasonably strong argument for using mobile CSP properly, rather than the sort of mobile use of conventional CSP. And the argument is made in a couple of diagrams here. If I was doing things, my model of the Klondike list would take the 3 processes representing 3 consecutive members of the linked list, or 3 cards, and we see each of these has got 2 links, one to the one up and one to the one down from it. And when a card moves out to be on top of D's here, then it takes quite a few interactions to piece together the remaining cards to look like this list here. Whereas you simply don't need as many parameters if you're handling mobile CSP, because A here doesn't need to know who's below it, because he knows he can communicate to B through his own unique linking channel. Whereas, and because that's mobile and is presently in B, it will give him the right form of communication. And it now turns out you can do things with a lot less parameters, and you can use less communications. You don't have to insert in this game, but if you did have to insert into a linked list, you'd get the same advantages. take another couple of minutes. Montana that we saw before, when you have this great array of cards, the argument for mobility is not so strong. So I want to talk about this just an example where somehow mobility doesn't seem to be as necessary. Because essentially the cards are laid out in an arrangement very like this. It's fixed for all time, a 13 by 4 array. Also, you're much less likely, because of the particular nature of that game, to find a lot of symmetric states. And a symmetric states would be one where you had the same cards in the rows, but the rows were permuted. And that's simply because in order to reach such states, you'd almost have had to solve this puzzle by the time you got there, if you think about the game for a minute. Furthermore, there are very few restrictions on who can be neighbours. In the linked list you get in the games we've seen so far, the neighbours are actually highly restricted if you actually think how the game evolves, but there's practically no restriction here. And that seems to mean that the mobile processors will have lots of states and a large alphabet. And in this particular case, despite my very considerable efforts, and if you see the number of files called mobile or Montana mobile n, where n is an integer, sometimes a large integer, it would indicate I've done a lot of work on this. I never did find a mobile model that worked remotely as well as my static model, much to my chagrin. But we did get some very, very interesting results with Montana, because it is a notoriously difficult game. Actually, if you look at the official rules, if there's such a thing as official rules, you find that it is indeed so difficult that when you get stuck, and you get stuck in that game, I should have said before, very important to realize when you get stuck in Montana. Hang on, I've gone back through it, I think, without even seeing it. You get stuck in Montana where all your spaces follow kings, like this. Because there's nothing which follows a king. So as soon as all 4 spaces you have follow kings like that one and that one do, you can't do any more, and the game's come to an end. Except that the standard rules allow you to pick up all the cards that aren't already in situ at the start of rows and deal them all out again. Now including the aces again, so you get your 4 spaces at random points again. And the rules would allow you to do that normally 3 times. When I was a child, my parents told me I could do that, but I didn't believe in it. I didn't believe it was necessary. Well, I shunned redeals as a child, so it struck me as cheating. But the web, if you look at it, tells you that only 10 to 20% of games are soluble, even with up to 3 redeals, whereas my models in FDR tell me that about 60% are soluble with no redeals at all, which I found really interesting. Maybe you don't, but I who had sweated over this game as a child and never got it out, was amazed to discover this result. If you think about it, the concept, on the one hand, of overturned cards, as in Klondike, and much more challengingly, the idea of a redeal in a game like this, creates some very interesting philosophical questions about what solvability means in these models. But they're questions that I have, fortunately, thanks to this result, been able to ignore. So, well, why did I do all this, and why am I telling you about this? Because actually the sort of techniques that I've developed for these card games are really only over the past 6 months. Actually point the way to handling something we've never been able to handle before in model checking software on FDR, which is how to handle heap and pointer structures. Because, of course, a very large proportion of practical software does involve these things. And exactly the same sort of structures evolve in these card games with the linked lists and that sort of thing, as will typically occur in the manipulation of heaps in real software. And our card game suggests that we can build up heaps from parallel farms of record processors which have the capability to point to one another. I shan't go of all the details of that. But there is one major difference between our patience models and heaps. Namely that we actually care, because they're vital to the game, what the card values are. I actually care that this is a 3 of clubs, and that's a 7 of spades. Whereas in paradigm uses of heaps and pointers, you will find that it doesn't matter at all whether I've got cell 17 here and cell 13 there, or vice versa. There's an actual symmetry in the use of pointers that simply is not there in the use of cards. And so, of course, we immediately realized in trying to develop these ideas as ways of handling pointer structures that we would need to find ways of factoring out that symmetry. So two states which are interreachable by bijections being applied to the names of pointers were clearly the same bijections, sort of swapping the values of the actual pointer cells that correspond, will usually be equivalent, an equivalence over such a program. And so this has led to us looking at sort of new symmetry reduction techniques to incorporate into FDR. And we refer to this as type-based symmetry, where you can use particular types, such as the type of pointers, in a very symmetric way, or where the use of those types within the program was highly symmetric. Because, of course, typically the only use you make of the pointer type is to summon new ones out of the ether, put them back into the ether, and use them for assignment and that sort of thing, and to compare them. So what I really wanted to say here is that puzzles can be really useful examples for developing programming styles. Because I think that, as I say, the styles which I've developed in, as I say, yet another class of games here are going to be crucial in extending FDR to deal with much more interesting ranges of software. Now, of course, one of the things that we did back in the 90s, when we first of all started to do cryptographic protocols into CSP, or rather to build CSP models of cryptographic protocols, was at least Gavin Lowe, who I talked about earlier, produced a compiler which automatically, given a abstract description of a cryptographic protocol, would generate the CSP file for you, so you didn't have to. And it strikes me it would be quite a nice project for an MSc student, but probably no more interesting than that, to do the same for a patience compiler here. So in other words, you need a language in which you describe games of patience. And you find there is actually quite an ontology of patience, if you'll forgive me from using a fashionable computer science word. In other words, a sort of standardized vocabulary of patient games which allows you to describe them. It's a whole new world. Anyway, our check here is still going. That's terrible. I'll see where it's got to. It will surely, hang on. It's gone, right. Still running, is it? Yeah. Now it's reached ply 39. So I really shouldn't have done it with 2 free cells. It's a very bad advert, but also just slowed down a lot. It's perhaps a little bit too. It's not too big for this laptop, but it's obviously. It's obvious that the last time I did try this particular check, I must have done it on the bigger machine I have at home, because this is going to take ages to finish at this sort of rate. But whereas the last time I tried it, I ran all 4 checks. I mean, certainly the last one took a while, but this one didn't. It all goes to show me the pitfalls that Peter was advising me of on their way over. We should never try a demo in a lecture. But as I say, I've got models of all these games of patience if anybody wants to see them. And if you actually look at my Montana game here, one. Well, I can't find which one I was looking at, but all I was going to show you was the long list of different random games that I'd tried, and which ones were soluble and which ones weren't. I can certainly find that for you later. So at any rate, for now I'm going to close down this embarrassing check and stop. Thanks very much.
Okay, thank you.